the size of the wolf population as it relates to the size of the caribou population. Before I get going there, let's write that equation down, okay? Let's write that equation down. So y hat equals a plus bx 22.361 plus 1.599x. As I said, you could use option 4 where it would look like it would reverse a and b. It'd be y hat equals 1.599x plus 22.361. I don't think you'll have to enter the hat on there. That's just the proper way to do it when you're doing regression. All right, here is the least squares regression model right there. That's the equation. Which is the explanatory variable and which is the response variable? So the explanatory, remember, is x. So the explanatory is x, okay? And what is x? X is the caribou population, the size of the caribou population. Caribou population, okay? And then the response is y. The response is the y, and that's the size of the wolf population. And I mean, if you want me to go back, I can go back and show you real quickly. Whatever you're trying to predict is your y from, we're going to predict the size of the wolf. So whatever you're trying to predict is your y. And then from, that'd be your x. That'd be explanatory variable, so the size of the wolf population. Okay. Can you use the equation? Okay, so can we use the equation? Yes, we can. So we can use this equation. Some things that I would say, it's kind of a weird question. Why can we use it? Well, I would look at a couple of things. I don't know if I have a stat plot on Zoom 9. I'll look at that. You see they've got a linear relationship, okay? And also, if I go back there, if I go run that regression again, the R value is strong. So this appears to be a good equation. That's a strong R value. So you could say, yes, we can use this equation to predict the y. I'm going to say y from a specified x value. What that means is I could use this to predict y, to predict the size of a wolf population from the size of a caribou population, okay? So I can use this equation. It's got a good R squared. We'll talk about R squared in a moment because I haven't even taught about that yet. The sample data pairs have x values ranging from 17 to 34. So that was my x's. If you want me to go kind of confirm that, I go look at my table. My lowest x is 17 and my highest value is 34. Those are my range of x's in my problem. To predict the size of a wolf population when the size is 21, will you be interpolating or extrapolating? Okay, now, what we do is if we're trying to evaluate for a value, we see if the value we're wanting to plug in is contained in this range of x values. Is 21 in between 17 and 34? Yes. So it's inside that range. So if it's inside that, we're going to call this interpolation. So this is interpolation. So interpolation, since 21 falls within the range of x values. Now, one thing I did not talk about yet, I need to talk about, I'm doing a lot of teaching on the fly here. Interpolation is good. So interpolation means we're plugging in a value inside that range because we have a trend from 17 to 34. So 21 fits that trend. Now, if you're plugging in a value outside of this, let's say I want to plug in 40 into this. If I wanted to plug in 40 into this, is that between 17 and 34? No. So 40 is outside of that. They call that extrapolation. Now, we say extrapolation is bad. Why is extrapolation bad? Because we cannot guarantee that this trend that we see on the scatter plot will continue for values beyond 17 to 34. So we can't guarantee this trend will continue. So when you do extrapolation, it's kind of frowned upon in the statistics community. Some people do it. I know we taught it in lower level high school math classes, but you're not really, extrapolation is not a wise thing to do. Interpolation is fine. Okay, so now let's go to look at the next one, which is not going to be that bad. Predict the size of a wolf when the caribou population is 21. So predict the size of a wolf. You're just using the equation here, and you're plugging in 21 is the caribou, so 21 is your x. So y hat equals 22.361 plus 1.599 times x, and you just plug in 21 into the equation. equation. Plug it into the model. And I'm going to need to come back to that because I want to talk about r squared. Okay, I did not do a good job of explaining this, or I'm setting this up in the notes. So 55.94. Now, if you want to, kind of a real world, they might have you round to the nearest whole number. So there's around 56 wolves. Okay, just round up. That would make sense because you wouldn't have 55.94 wolves. You predict around, if the caribou population is around 21, you'd predict around 56 wolves, okay? This Y hat means it's not going to be exact. It might not be exactly 56, but that's going to be our best guess. Now, one thing I did not cover, okay, and I'm going to talk about this in the homework as well, was r squared. R squared is the coefficient of determination, okay, so 0.837. By the way, you never ever express r as a percent, but you often express r squared as a percent. So this is 0.83725 means 83.73% of the variation. What this means is 83.73% of the variation in Y in the wolf population can be explained by this model, can be explained by the linear relationship between the caribou and the wolf population. So there's another approximately 16-17%, because 100% is a total. That's just other things that might be accounting for the variation in the values. Okay, so on there, you're gonna, on your homework, you're gonna have to say what percent of the variation is accounted for by the model. You'll say 83.73%, and what's not accounted for by the model, it'd be 100% minus that. So it'd be 16.28% is not accounted for. So that's unaccounted for, as I said, and those are type of things that are that's just random chance or probability. There might be some lurking variable out there that's influencing the Y outside of just the wolf population.